Yo, yo! Okay, on today's VOD, we were looking at trying to gain an understanding of how quaternions work. We are working on a game, I guess you could call it. We don't really know if we're going to turn it into a game, but we have this little character that we've animated. Look at him. Look at him go. He's so pretty. He's running around. And we want to like import this guy into a game engine, right? And by a game engine, I mean like our game engine. There's a lot of quotes going around here, right? But we basically want to import this guy into some OpenGL world, right? And to get there, we have to like take this mesh that we have. Can we select the right guy so that it looks this one, this one, this one? Yeah. So we want to take like this mesh of this guy we have, and we need to like apply some transformation to make him look like these bones, right? If we like look at the animation that we're running, it's this is the actual thing, right? And so we need to import all of these bones and their rotations and how they change over time, interpolate between them, get them into our game, right? And we were looking at this export of this guy, and we noticed that, like, in the GLTF export, these rotations are sets of 4 numbers, which at this point I haven't double checked, but I'm assuming that these are quaternions, right? And I don't really understand quaternions at all. Like, really, very much at all. I've watched like a few videos, and like I understand that they're like kind of encoding an axis angle representation of some rotation, and that they're like nicely lerpable, and something about hypersphere in 4 dimensions, right? Like these are concepts that I have in my head, but I don't really know how they work, right? So the goal for today's stream was to write some sort of visualizer where I can kind of like inject the different parameters as well as like adjust them to their constraints. My idea was that we want to have some sort of like 3D ball that you can kind of like in the ball set the axis of rotation as well as like maybe a slider that says like how much rotation you're going to have, and that would generate kind of maybe your X, Y, Z, W quaternion, which has some sort of like math about like cosine theta on some real part plus sine theta on some imaginary part. I don't really know. But anyways, I'm just recording this now because I think that the intro to the stream, I wasn't really expecting to post this in a way that needed to be reasoned. So just for when you guys jump in, you're like, what the hell is he talking about? This is what we're trying to do. We're trying to build this visualizer. And we spent most of the stream today trying to actually build this part. So go enjoy. See you guys in a bit. I guess the first thing to do here is we probably want to yoinkies the latest and greatest of our SFIMP repos that we can get on Zig 014. We have some like 3D math changes that we've made here. Like so the way that like we are set up is that our OpenGL app kind of depends on the image editor because like the image editor is like where all our dependencies live, like window management and like math library and like OpenGL stuff. So it's kind of easier to work on top of that. So the other day we upgraded to Zig 014, which we should be able to just like get rebase master, and we should just get the latest and greatest, I think. We'll just call this shit blob RTS. There we go. Okay. So we get into our Zig env. Works really nice in any number of dimensions. Yeah, that's cool. That sounds kind of neat. Okay. Okay. So does this still build? We'll just make sure that we're in like, oh, okay. Not quite. Not quite. This guy needs to get the Zig 014 treatment. So he's going to complain that there's no fingerprint, and we just kind of slap this guy in here. Uh-huh. Okay, now do we build? We come hype. Quaternion is magic. Nobody knows how it works, but it works. I don't think that's true. I watched that like 3 blue 1 brown video on it, and it seemed like it kind of like he kind of had something that made sense. All right, cool. So yeah, what's like the plan? Probably we're going to I want to render like Okay, so what do we know so far? What do we know? We should start here. Quaternions. Quaternions. What do we know? My understanding from that, like, from 3 blue, 1 brown video, uh, they kind of, rotations, I guess we just start with, 4 numbers. Quaternions, 4 numbers. 4 numbers represent any 3D rotation. We also know that they're like nicely interpolatable. Nicely interpolatable. I don't really understand how yet. From 3 blue 1 brown video, like quaternions are like some yeah, something about a 4D hypersphere. All rotations are at radius 1 on this thing. Okay? That's kind of like the level of knowledge. Oh yeah, and I've also read somewhere that like semi-equivalent, like somehow they represent axis angle, question mark? I think I read that on the Wikipedia page. Does this talk about like rotations? Quaternions in 3-dimensional geometry. The vector part of a quaternion can be interpreted as a coordinate vector in R3. Therefore, the algebraic operations, blah blah blah, operations such as dot and cross product can be defined in terms of quaternions. Sure, but I think I read somewhere that the quaternions are like represented as 4 numbers. There's like a real part and then like an imaginary part. You have like these like magic rules for how like the imaginary parts multiply together. This table here, right? So like in the same way that you have like imaginary number I, and you know it, you can multiply by itself to get -1. You have like this like ijk where like I times j times k equals -1, and then like multiplying I times k gives you j or something. I k gives you j, yeah, and then like ij gives you -k. Yeah, there's like all these rules. So there's some sort of like mathematical properties. I'm not really gonna worry too much about them. I'm more worried about like what the fuck the quaternion is, right? But like, so they're like, okay, so in the same way, we're learning about quaternions today? Kind of. I don't know about learning is learning strong. Playing with is probably more accurate. So like, you know, when you work with like imaginary numbers, you sometimes like draw this as like the imaginary axis I, and then like the real axis 1. And then like you can like draw rotations on this thing. My understanding are like quaternions are like a way of doing this in 3D. That's kind of like hand wavy. What my understanding is. Nice video you can watch after stream. Is it the 3 blue 1 brown one? No. Okay, nice. I will bookmark this and maybe take a look at it later. Okay. So what else? Yeah, where did I see like axis? Yeah, here. Here somewhere they're talking about like the axis of rotation being the vector part. So like math speak. Wikipedia has a different article. Oh, maybe that's where I was confused. Where I was reading this. Yeah, this is probably where I was looking. This looks more familiar. Yes. Any rotation in 3 dimensions can be represented by a vector and an angle. Yes. So a rotation of theta around this vector can be represented as this thing, and then they somewhere talked about like the axis being the imaginary part. I thought. Maybe not. Let's read a little slower. Euler axis is typically represented by a unit vector, this E in the picture, the blue thing. Therefore, any rotation in 3 dimensions can be represented as axis angle, blah, blah, blah. Quaternions give a simple way to encode this axis angle representation. Yes. Yes. Okay. So Somehow they represent axis angle? Yes. Okay. What was I going to say about math speak? I don't remember. Um. So yeah, somehow they're representing axis angle. Somehow. And so I guess with that piece of knowledge, I want to like. Oh yeah, then there's something about like the real and the imaginary part. I think I saw something about like as you get more and more towards the imaginary part, the rotation happens more and more or something. And you're always kind of expressing your equation as this, where you have real part is cosine theta over 2, and then you have your axis multiplied by sine theta over 2. So like this will always add to 1, I believe, which means that it's a point on some 4D sphere. The last part of the second paragraph from the top. Oh, the axis angle stuff, yeah. Um yeah, so there's like something about this where you're like you're on some 4-dimensional sphere because you're always 1 unit away from the center. And somehow like the real part, the real to imaginary ratio is like how much of the rotation it is or something. Maybe? I don't know. I don't know. But I kind of figure um I want like some visualizer that lets us play with the vector. Thanks to the Prime. I don't want you to stop making content. Hey, thanks, man. The Prime helps. Much appreciated. Some visualizer lets us play with the vector and real to imaginary ratio. I feel like this will give me some intuition. Right? Then we can like set the vector by clicking in some way and then like move some slider to see how the like angle part around that vector changes. And then maybe as we can like play with lerping as well. Yeah, sure. Sure. Oh yeah, math, like the math works out here. Oh, so that they can interpolate well. Yeah, okay. You can tell I'm like not very this isn't well reasoned or well thought through or well researched. So we'll figure it out. So I guess we want to make some widget that lets us set a 3D vector. I'm also implementing my own engine using Zig using WebGPU API. API support for meshes, materials, and instance rendering. Hell yeah, dude. Yeah, let's start there. Like axis unit vector 3D setter. Then like slider to change real imaginary ratio or something or angle. And then I don't know, play with it and see what it means. Maybe try lerping. Slurping, as they call it, because it's spherical lerping. Yeah, okay. Let's just start playing around. So we have our guy. We have our, like, this is our current state, where we have our ability to import some 3D model in and, like, display them in OpenGL land. So for now, I guess we're going to comment this guy out. And what are we going to do? We probably want, like, camera movement first, to be honest. In test setup. Yeah, let's try that first, I think. At the very least, we want to be able to, like, rotate and, like, see things from different angles, I think. So let's maybe start there. Let's start there. So, I don't know, man. How do we get the shit out of this guy? I think it's just like read. This will tell us like an input event. Read item. Yeah, okay. So while window q read item, this should give us some like input event. And we should be able to do something like this, like interpret mouse movements and mouse clicks. Probably. Probably. I don't know, man. Normal colors are the best colors. Yeah, I mean, it's because I haven't written like a fragment shader yet or done like texture mapping from GLTF or anything. So we're just kind of like sitting there. Okay, so if mouse down, we do like rotating true, I guess. When the mouse goes up, rotating is false. And then we probably want like on mouse move. We're gonna do something with the movement. Yeah. So we probably have like, you know, some like probably X rotation and Y rotation. And here, can we just say like X rot plus equals movement X and Y plus equals movement Y? And then we like apply those rotations to some camera transform. Okay, so here we probably like generate the transform that we're using to render this guy every frame. And we start with Y rotation, then do like an X rotation. Oopsies. I think it's we've got this backwards, I think. We want to rotate around which axes do we have? We have like Y, X, Z. And when I move my mouse left and right, I want to rotate around the Y axis. And when I move it up and down, I want to move it around the X axis. Sure. Sure. So rotate. We'll do X then Y, I guess. And then this stuff goes away and then we apply perspective. All right, let's see if that does something to let us like look around. That's not good. So here we have to do this if rotating. And then I think we kind of also unconditionally want to be like kind of a little bit farther back from the guy. So can we just kind of move a little bit back in Z or something? Wrong way, maybe? Okay. That's definitely doing something. Let's get a little bit slower. Holy shit. What is the like? Okay, too slow? Am I? Okay, let's only do rotation around Y for a second. Oh, maybe this is backwards. Rotate X, X rot, but then let's only do that for a second. So no matter which way I move, we move in the same direction for some fucking reason. Am I brain dead? What are we doing wrong here? Yeah, what the fuck? It only goes up. What the fuck? You're rotating X, sure, but like no matter what the mouse movement is in a circle, we're seeing like the same. He's moving the same direction, right? So you want the difference between. Oh, that's probably what. Yeah, well, mouse movement. This movement should be relative. But you're right that we should look at what this thing is. We should at the very least look. Ah, it's position. Okay. You are right. Last X. Sure, whatever. It doesn't fucking matter. That's what I thought. Yeah, me too. I mean, you were going off what I what I put there. What is mouse pause? This from? Where is this coming from? What is this thing? Mouse move, mouse pause is from GUI. Ah, okay. Sure. So that means that we need the GUI framework here. That's kind of weird. That feels maybe kind of wrong, but whatever. Like we need our GUI framework to do any to do like any input handling in our windowing system. Doesn't sound right. Doesn't sound right. But whatever. Okay. Then we should be doing like last pause like this. All right, let's see what that does. Fuck. All right. We need UI. What does movement encode then? Do we have an ill-placed absor? I think it's like the pixel position in the window. So really, we should probably like normalize it and stuff too. Programmers' presuppositions are causing most bugs. Yeah, for real, dude. Okay. Does this do something? Okay, so now it's just like way too slow, maybe? There we go. That looks like, I mean, that's too slow again, but it's starting to resemble something. Okay, we may go like 10x that speed. There we go. There we go, baby. Okay. We'll do the same thing here, and then let's just, it doesn't have to feel great, it just has to feel like good enough. Having your own math window, alloc, and render library is crazy work. Yeah, I mean, the window one is kind of cheating. Because the window one is just a wrapper around GLFW. But the rest are, I think, fair. This has to be last minus pause. It's upside down. All right, there we go. So we got, I want to maybe zoom on scroll too. So maybe we do something like this, where we'll say scroll. Do you guys think it's amount, or do you think it's, this one has to be relative, right? It's gotta be. Okay, what the fuck is this thing? Because clearly whatever we're doing is fucking stupid. It's always 1.5 or negative 1.5. So why is he flipping? when I'm going in one direction. Oh, because field of view is right. It's like a rotation. It's like an angle. So we need to do like maybe like if amount is less than 0, FOV. If we're going down, then we want the to zoom out, which means that the angle is getting wider, which means FOV times equals amount. And we probably just want to cap this guy. If FOV is greater than equal to stood math pi over 2, like over, yeah, something like this. And then, sure. And then this probably, we probably need to scale this. Probably, but that seems like it might take us somewhere. Don't you want to translate? No, because I want to keep the camera in the same spot and just like zoom in. I think. Zooming out is still not working the way I would expect. Zooming in kind of works now. This is kind of behaving. But zooming out is like, I don't know what the fuck that's doing. Maybe this is the broken one? Negative 1.5. Yeah, so this is, zooming out is down. Oh. Oops. Yeah, there we go. There we go, baby. That's good enough. We could scale this a little bit, but that's fine. We don't need to get more advanced than this. That's just good enough. Okay, so now we can like look at stuff, which should help us with making a unit vector like setter. So what I'm like imagining is like we have like maybe red like X, Y, Z axes that we have like maybe like some sort of like sphere around and like some arrow that is like pointing, you know, towards some point on this sphere. And you can like kind of rotate this thing around and click on the sphere at points, and then like the arrow will go there. You know? That's kind of what I'm imagining. But I don't really know. So how the fuck do we do that? Do we just need to generate a sphere out of triangles? I guess so. Maybe we start with the axes so that because like that I know how to do. We want to. I guess we don't really have like a GL lines abstraction. But maybe we don't really need it. So we have some world space, and we just want to like put the axes in the world somehow. Yeah. So I guess we just make a program, like a little shader program to do that. Seems kind of reasonable. How do we use these shader programs? I think we have like an abstraction around these things that like is relatively easy to use. So can we say like line program? This is gonna be like a line vertex, and the line vertex is going to have a position and a color, I guess. I guess technically v norm is already a color. And yeah, sure, fuck it. I don't know. And he gets the same transform as this guy, so his uniform is going to be the same. And we're going to have like line vertex shader and line fragment shader, which probably the fragment shader is the. We can probably cheat and use the same program here, actually. Because we're coloring according to the normals right now, so we can just lie. Which is kind of funny. So that means that like we can probably just reuse the existing program to render these things. It's just kind of funny. So we can say this is like axis buff. Yeah. And so it's like the v pause is equal to one thing, and the v norm is equal to like 1 0 0 for red, which means we're gonna be going from like one like negative like 1,000 to 1,000 or something, right? Surely. I wonder. I don't know if you can use like infinities here. If OpenGL will handle that well, we could find out. I would expect no. But yeah, we'll see. Okay, so let's render the axis buffer first with this thing. Except we don't want to render as triangles. We want to render as lines, which we don't really support doing right now in here. But this is easy to fix. This just needs to support like taking in something. Yeah, we'll do something like this. Mode is, mode, I guess. And we'll say that we can be, triangles, lines. Actually, we don't even need this. This can just be like the OpenGL value. GLenum. What features does your math library have? Not a lot. It's literally just like wrappers around like 3x3 matrix, 4x4 matrix, and then like a couple matrix multiplications, 3D transforms, 2D transforms, and then like cross product, dot product, and stuff. So it's not a lot. It's just there so I don't have to rewrite the same fucking thing every time. Am I stupid? Why isn't this working? Okay. So this guy takes in this stuff. And this is like GL triangles is kind of like the default here, and then now we use mode down here, and then we support like render lines now that calls this stuff, but with lines here. I haven't been able to catch the stream for a long time. What is usually the subject of being built? It's pretty scrambled. We've been working on our image editor a lot, Right now we're kind of like experimenting with the idea of making like a game. We'll put it in quotes. We're playing with like an animation. We're working towards like an animation system for this guy. So we have like a thing in Blender of this guy running. Where you have this guy, right? We've made this little animation, and we want to import this into like a game, and so we have to like uh take the exported animations that are using like quaternions and like figure out how to like apply those to the bones and how to apply those bones to the mesh and stuff. But before we do that, we have to understand like what the fuck the rotation is at all. So that's what we're trying to do today. Okay, so now we should be able to draw that red line if we go over here and we say render lines like this. I'm hoping to see a red line on the x-axis, which we are. It's just that our guy's facing sideways, so that's kind of hype. That's kind of hype. So let's do. And then what happens? Like, I assume that this breaks stuff, but if we type like std math inf here, I assume that that causes problems. But if it doesn't, that's kind of hype. Yeah, that's not okay. So we need some like scale of the world. I guess arguably you could just not scale it or something, but sure. I mean, that's good enough. Okay. So let's add the green and blue axes here. Like this, and then this is now this axis and this axis. There we go. Although this feels wrong. R G B. Yeah. Oh no, that is right. That is right. So when I have X, Y, Z goes into the screen. Yeah, and it's confusing because he's facing sideways. I'm used to facing him this way. And then I'm also used to in Blender, the Z axis is up, which is also throwing me off. But this is what I wanted. This is what I wanted. So now what? I guess we try to draw the sphere, which is like, how the fuck do you render a sphere? We could like take a bunch of triangles and try to like construct a sphere out of them, but that feels like kind of wrong. Like a little bit. I guess we could just not render the sphere. That kind of solves the problem for me initially. So, we should probably render it, but we could do that later. So what's like the first thing? Let's like maybe get the unit arrow in there, and then we can kind of figure out more later. So I guess we need like an arrow to render. So like, can we just kind of make one? The 3 stages of rendering a sphere. How do I render this? I guess we can use triangles. Maybe we just shouldn't render it. Is this part of the GLTF importer? We are using the GLTF importer here. I don't know if I would say it's part of it. Cylinder. So I guess we take these guys and we just manually set them at Z0. Then we take these guys and we probably set them... I guess we take this guy and we set this guy to Z1, which means that all of these guys need to come down below him, which means these guys also need to come in here, and then this arrow's fat as fuck, so we kind of scale him so that he looks less like shit, and then I think that I actually want all of this stuff to kind of come up like this. Sure. There we go. There's an arrow, if I've ever seen one. And I guess now we can export this. And we have like GLTF importing, so I guess we just use this and we say this is going to be arrow. Continuing on the geometric math topic, setting w equals 0 might result in points at infinity. Yeah, I think that makes sense. Because what? I don't know the math yet, but I believe that does line up with like things I've seen before. We can create the sphere in Blender too. Yeah, we could do that. I just thought like why? I guess because it's just like if you do this, it's like that's not a sphere, you know? It's like that's a bunch of triangles. So it means that like, but like for visualizing, I guess it doesn't really matter. Right? If we just do this, you know, that's like, you know, maybe fine. Maybe. But I'm going to come back to that. I'm going to come back to it. Export. Did we save this already? Okay, so we should be able to like get some sort of like arrow model in here. So we'll call this like arrow model is load GLTF from path. So we were loading untitled GLTF, and now we're loading arrow GLTF. And can we just replace right now model with arrow model just to see? Okay, promising. That's an arrow. We probably don't want to color this arrow that way, but for now, that's fine. Then let's try to figure out, like, when we click somewhere, we want the arrow to, like, point towards where we clicked. Which is, like, what? You can see the rotation. You can set the rotation mode in Blender to quaternions too, so they can be reasoned with from the Dropbox. Yeah, I've seen that. But I think that their quaternion thing, like playing with it, like they allow you to kind of do things that, like they're doing something here. I don't know what. They're probably normalizing the XY component. Like they're doing some sort of normalization here. I don't know what it is, but you can see like you can like drag forever. But anyways, doing it this way allows me to implement the quaternion math as well, which is like something I need to do anyways. So it's kind of like a nice excuse. The fuck is W? That's what I'm saying, dude. Okay, so if we want to like click somewhere and have the arrow point at it, it means that like according to our camera's like taking the world and like applying perspective on it, right? We kind of have like some like sort of, you know, if this is like a 2D cross section of where we're looking, where like this is like far away, it means that like as we click anywhere on here, we're kind of like clicking on all of these pixels at once, right? If we click on the screen, we're kind of clicking through all of these, or through all of these, or through all of these, or through all of these. And so if we want to know where the arrow should point, I guess you have like a sphere over here somewhere. I guess the sphere is like inside this like this thing. And we need to figure out where our fucking like the ray that we're sending out like hits the circle. I guess. Which is like, how the fuck do you do that? I guess you have the equation of a line in 3D space, right? This is like some sort of like, there's something here. You know, like where the 2 points of this line are relative to the center of the circle, probably, maybe. So you have like in 2D, circle, line. Where are these points? You have like x squared plus y squared is equal to 1, is like the equation for the circle. Then what else do you have? And so in 3D, I assume this is just plus z squared. I assume. Then what? Maybe that's harder. Wait, hold on. Okay, so if I am a sphere, this is a sphere. Arrow coming through sphere. You can tell the radius of the sphere at this height, right? Like as you move up, the rings of the sphere get smaller and smaller and smaller and smaller, right? So the but this is assuming that the arrow is going straight, which I don't know if it is. Hmm, that doesn't seem that doesn't seem like super obvious, right? I could be shooting the arrow. We could be looking from like up here and shooting down like this, right? So there needs to be some sort of like collision check. I guess it's like, what are we looking for? We're looking for this point, which is defined relative to the center of the circle as like this. So like, we could be shooting down here and then we're looking for this. We know this point. This is where the camera is. We know probably we know this line. Certainly we know that. And so that means that we don't know the direction of this arrow though. We just know the length of it. So this is like an unknown angle. Am I like fucking stupid? I feel like it should be easy to figure out where where a line collides the sphere. But maybe it's not that simple. We could look it up. I don't know if I'm gonna like be able to like deduce the answer very easily here. I don't think. This feels like one of those older SAT questions. um yeah. There's something probably about like the curvature of this thing that we can leverage as well. Okay, like we could think about it at the limit. At the limit, we have sphere and like we have some cone where this is no longer valid, right? That's probably useful information. So there's like some angle here. We know kind of like what the angle of our ray from the center is, probably. So we have all of this information. And then probably where we collide has something to do with like you hmm there's something here. There's something here where you kind of also know for sure where like on this line you're hitting, which must be some useful piece of information, right? Because then all you have to do is map this, which is easy. No, untrue. Untrue. You're mapping something more complex than that. Ray tracing, no? Yeah, yes. Right? But I don't want to look at the I want to see if I can figure it out. I want to see if I can figure it out. Because like when you're saying ray tracing, like to trace the ray, I mean you could just step, right? You could just like fucking like do a binary search. which would get you like an approximately correct answer. But surely there's like some like simple mathematically correct answer. The collision comes from a point we are trying to see where on the sphere the point is. I'm trying to click on the screen and point an arrow at the point on the circle that I clicked. That was kind of what I was imagining. That's what I was imagining, but yeah, I mean, you're right that you could just like check steps of the arrow, of like the ray. Just intersect ray and circle, but that's what I'm trying to figure out. If you want reference, you can compute things in order that they are numbered. Arrows are vec3, lines are floats. You compute things in order that they are numbered. I don't even understand what you're saying, but I will click this because why the fuck not? Oh, I see. Oh, you're just giving me the answer. Fine. We'll see if this makes sense. Okay, come on. I was getting kind of close here though. I was looking at this line here, 3. I was looking at that. Except I was looking at these as well. So what, you're saying like, right, you just project onto the direction of this guy. So this makes sense. Me to the center of the circle. Then I guess we have this, do we? I guess you can kind of like restructure whatever you're looking at in terms so that that line is flat. But I don't think it necessarily is. Right? If we're cameras here, circle here. I'm just trying to like think about this a little bit. Okay. So here we have. Oh, you're saying you have this is all. You always have some perpendicular line here. Sure. So you have like normal to this. Normal to the direction of your line. You have some other line. Yeah. Makes sense. So that's 90 degrees. Then you can project this onto that, and you know this distance. But then we're still missing this part, which is what you were talking about. This 4. And we're looking for, I guess, kind of this thing. Because this is the final answer we're looking for, is this arrow from the center to wherever it intersected. Oh, I see. And do we know, like in this picture, do we know either of these distances? We don't know this angle. We know this radius. Oh, we know 3. We know this. So between this line and this line, we can calculate this line. Which should give us everything we need. I'm pretty sure. Yeah, I see. I think that makes sense. How does this extend into three dimensions? Because yes, I think it does. Because then we have the point on the sphere, which is the direction of the vector multiplied by the distance, this green distance. Yep, that makes sense. That makes sense. Okay, let's try that. So, I guess let's start with rendering a point on a sphere. Oh no, we can just how do we like we need to rotate the we need to rotate the model of the arrow in some way. Right? So we have kind of like our viewport transform. But can we take this thing who is normally pointing at 0, 0, 1. No, 0, 1, 0. He's usually pointing up in Y. And we need to find the rotation matrix that points him at a particular point. So can we like set like unit dir is going to be 010 or something, right? Do we have a look at function? We might. Rotate A to B. We have this in 2D, but not in 3D. Oh, that's going to be annoying. So basically, you just where your point intersects within the bounds of the sphere, you map the sphere drawing triangles, or no? I'm not really sure what you mean. Where do I don't think there are any triangles coming into play here. I don't think. But I could be wrong. Okay, so you have some guy. He's pointing this way, and we're like, we want you to point this way now. How do we like determine what that rotation matrix is? This angle probably, like, this is in 3D, so we probably have like I guess there's one angle and some axis that he's rotating over. We're back into like the original problem of quaternions. So you can probably rotate over either axis by this angle, right? So like if we're pointing like if we want to do this as Euler rotations, can we get like XYZ Euler? We can rotate over like just the x-axis unconditionally to get to like some rotation this way, and then we just have to rotate this around z, the like upright angle, until it points to the right spot. That seems reasonable. So the rotation around x here is purely based off of the height. Yes. So you have this, you have some point. How are we representing this thing? We're going to have some point on the sphere in XYZ. Yes. So we have some y value here. This rotation is going to be what? Like, as this moves down, it's got to be something like sine x or sine theta, probably cosine theta. Because like, yeah, that feels right. Maybe cos theta. Because here it starts at 1. Y is going to be 1 here on this line. It's going to be 0 here. And there's some sort of like angle-based thing. You can do Euler decomposition, but you'll run into funny things. Yeah, but I don't really know how to do like a proper look at, which seems harder to me. So doing Euler decomposition, like I can reason about this, and it doesn't really matter because we have like these extra constraints. What do we do in 2D for look at? Rotate A to B. Interesting. Oh, but in 2D it's a much simpler problem. In 2D it's literally just like what is the angle between these guys? Rotate that much. So that's why it's simpler there. Yeah, I think this makes sense. So we're probably doing what? Cosine cos 90. Oops. Pi over 2. 0. And then sine turns into 1. So our rotation We've got to be using sine here. We gotta be. We gotta be. So we're gonna do like arrow transform is gonna be like we're gonna rotate around the x-axis by sine of unit der 1 minus this, maybe? There's something here where this has to be like multiplied by. We probably want like 1 minus this so that the rotation gets bigger as it gets farther. And then this needs to be multiplied by pi? That sounds right. To make it so that it goes like the full amount in. We have like y rotates 2. Oh, so right. We're doing like y difference could be up to 2. Column's rotation matrix is blah blah blah, so you can make an arrow from the neutral facing of plus x. Oh, that's a really good point. Now that you've said that, you're making me sound stupid. Yeah, that does seem really simple when you put it that way. Because that is just a better answer. So we have it pointed at y, which kind of fucks this shit up a little bit. But you could just rotate it down to point at x, then do. Well, okay, let's think. Let me think for a second. Columns of rotation matrix is where x equals 1, y equals 1, z equals 1. True. Let's see if we can reason about that. So you have like rotation matrix vector, right? So you have like x, y, z. So x gets multiplied by here, here, and here. X, 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 y, 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 z, 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 right? And so we want y1 to look at some particular point in here, which means that like you just put the point here, but then what do you do with the x and the z? Because I think that there are other constraints that you have to satisfy here. Right, because if you want y to look at like, I guess it's that you have, I'm not quite there. Not quite there. You're saying with the rest of it being identity? Is that true? Because you have to have. I don't think that's quite right. Because don't like rotation matrix. Don't you have every row has to add to 1 and every column has to add to 1? I thought that's what it was. Right, like. So because we need to keep like the shape of the cylinder, right? But I think that you're onto something with you saying just like point y at the fucking spot. That makes a lot of sense. So I think that you point y at, you fill in this thing so that y is the thing, your vector, and then you just solve for the rest probably. Because like we're trying to prevent like warping of the cylinder at the bottom, right? Like, because in this thing, these like the xz plane here needs to like stay correct. Your intuition of look at is my thing, but done correctly. Oh, just like like doing the decomposition that I was doing before. It seems like you're close though. Like the idea of just like hucking the y values in there, it's like kind of right. But yeah, you do have to. I think that you. I just don't know how you keep the XZ plane looking correct. So fuck it, we will do it this way because I was basically there. I think. So it was. I don't think I was basically there, but we were close. So what do we have here? We have circle. We have point. Y. You know. We have 1.0, right? And we are trying to find the angle from perpendicular. This is what we're trying to find. Which is this here. And which means that we have this value. This is y as well. Right. So this is sine so we have cosine theta, I guess, is opposite over or adjacent over hypotenuse. This is equal to y. Y over 1, because the hypotenuse is 1. So this is y. Which means that if we want the angle, we have to do the opposite, like just a cos of y. But is y the right answer here? Yes. Because angle is 0 when y is 1. Cos 0 is 1. Yeah, okay. Yep. So we just do rotate around x by a cos of the y position of this guy. Okay, and so that solves the first half of the problem. Now the second half of the problem is that looking top down, compute the rotation matrix corresponding to the quaternion using. Yeah, I'm not there yet. It looks like we're there because we're talking about quaternions, but we're actually just doing like there's no quaternions happening at this exact point. We're just trying to like set up the test case to build out the quaternion math. Right now, we're just trying to like build a sphere that you can click on to set the direction of an arrow because we're trying to build the visualization. So this was y and z, I guess. This was the z-axis, this was the y-axis. Now we're looking top down. After we've done this rotation, we've rotated around x. So this is x, and we have some arrow that's pointing probably towards z, or yeah, towards z, I guess, by some amount. And we are trying to rotate it to some other angle, right? Now, how are these known? So, presumably the lengths of these guys are the same. They have to be because we've rotated by the right amount. Then, let's think. We have this and we have this. We just have those two numbers. Which means that this angle is just this angle because it makes like a little z. So tan theta is opposite over adjacent, which is x over z. So we just do like a tan 2 xz, maybe? Maybe. That's like definitely a possibly correct answer. So can we apply on when we render the arrow, we take the arrow transform, then apply the viewport transform? And then we'll start him at 0, 1, 0. So point him up in Y. One sec. What font are they using? It's Sonokai in Vim, but with term GUI colors off. Okay, so he's pointing in Y. That's good. If we point him in X now, font, I don't know. I'm not gonna check. Oh, let's fucking go. That's pointing along X. See, he's on the red arrow now, and then we put him on the fucking blue axis. Boom, baby. Let's go. I love it when shit works. Look at that. Look at that. That's a fucking arrow that points at a spot now. So now if we wanted to point at like 1, 1, 1. Oh, that's not good. That's not working. So why not? Why doesn't this work? Because this needs to be a normalized vector. That's why. Do we not have a normalized? Normalize. Let's go, dude. That went smoother than I thought it would. Okay. I'm realizing now. So now that we can like point it at anywhere, we can go back to trying to make it so that when we click on somewhere, he follows where we click. Right? So did we lose our context on that? No. It was this stuff. So we calculate the vector from the camera origin to the point of the center of the sphere. We also need this vector, whatever the fuck this is. So like when we click on the screen, I don't really know what that is. So we have like some fields of view, I guess. And we have a line that goes like infinitely long along something. I guess we could pretend that there is some plane really far away, and we could calculate the point on that plane that we clicked on, given this FOV. Yeah, that seems reasonable. So this is like a known distance here. This vector. Z will just say is like 1,000 or 100 or something. It doesn't fucking matter. It just has to be farther than the circle. Then we have field of view. I guess we need to take. We know where we click in pixels, which is kind of fucking weird. So I guess we need the ratio. Like this is gonna be like 0. This is gonna be like 800, right? And so if we want to know where we are relative to the center, I guess we need to convert this so that this is 1, this is -1, and this is 0 or something. That's like a coordinate space that makes sense to me. So I guess let me think. We're so close. I feel like all of the pieces are there. We just have to like shuffle them into the right spots. So we have unitless. Everything here is like unitless other than angle. We have some angle. And we have this in pixels, right? So this is going to be like 0. This is going to be 800. So if we want to calculate the angle, we know that this distance is 400. This is 400. And then this is anatan 2, opposite over adjacent. But we don't have adjacent. But we can make up adjacent. We don't even need it. Because we have the angle. The angle already exists. That's what I was missing. The angle already exists. So if we want to construct a vector from that angle, I guess there's also a piece missing here where this is like not axis aligned anyway in any way. We have like a transform that's like where the viewport is looking. Like we kind of do this to the world. So from the center of the sphere's perspective, we probably have to like invert that. So we probably want like camera position is kind of like the first three parts of this. Then the viewport transform is the camera position followed by a perspective, which makes sense. And then to get so we have like this ray in like camera viewport space. So that means that if we want like camera to world, we need to take like the camera position matrix and invert it. Do we not have that? I swear we did inversion. Only on a 2x2 matrix though. Oh no, we have 3x3. Oh, we need to. Does that mean we need to invert a 4x4 matrix? That's annoying. Because we don't have the math for that yet. Maybe not. Because we could do this in terms of knowing. We kind of know that the camera is some distance back from the sphere. And we have the rotation. So we could just like do the backwards rotation. And then we only have to invert the 3x3 matrix. Then what? Dude, 3D math is fun. It's just so much just like trying to build the tools that you have into something usable. Okay, so we are a camera. Let's pretend the camera is just pointing straight for now. Because I suspect there's also something that we can abuse that's like the thing is a sphere, so we can probably just rotate the point by the camera rotation or something afterwards. Yeah, let's start there. Let's start there because I don't want to think too hard about it. So let's just see if we can figure out, assuming the camera is like on an axis, let's just pretend camera is sitting right here on the x-axis, pointing backwards this way at the sphere. We are trying to find the vector of where we click on some back surface. Because we need some sort of like bounds on this vector for the math to work, maybe. Maybe we don't. We might not. We might only need the direction, actually. Let me think about that again. Where's that picture that Urkerstuna drew earlier? This. Yeah, we don't. This thing doesn't need a length. Which I was just missing. This is just a direction. Which is hype. Okay, so if we want a direction, we have an angle. I think. Yeah. Yeah. Surely. So the direction, say that we're looking like forwards on Z, that means that we need like an X and Y direction out of this somehow. So it must just be like X is equal to what? I'm so confused. Thinking about it in 2D, it makes sense, right? You're like, I have angle of view and I've clicked somewhere and I need to rotate around x, like rotate, x squared, x plus y plus z squared is equal to 1. That's one constraint that we know we have. The line has to be unit length. All three of these parameters are going to move. Yes. But we have the x and y offsets from something. Because we have like a window that's like 800 wide and 800 tall. So if I click on like 400, 400, like what does that mean? Right? Where we click on here, we click on 400, 400. That needs to turn into some sort of like 3D vector, right? Here that goes through. Is that it? So we have like 0, 0. We know that we go through like these 2 points. Boom. If the size, it's probably like you set the distance of this to be 1. Yes. So z is always 1.0 or something, and then you just normalize after. And then you set the units of x such that this is FOV. Then if you're at 0, 0, you're at just z distance 1, and if you're anywhere farther, you just have normalized again. Yeah, fuck it. Okay. So it's like z equals 1. We need to basically map 0 to 800 to FOV. Because then you have like tan FOV is equal to FOV over 2 needs to be x over z. Yes. Is this what crazy people draw on walls? Yeah, we're definitely approaching that point. Yeah, we need to scale the back plane that we're like projected, that we're looking at, so that this distance over 1, so we're setting z to 1, which means this is just x. This has to, and we have FOV. Oh, sure. We have FOV. So we just calculate this. We calculate this. So we need to make it so that like 800, pix width needs to be multiplied by pix width over 2 has to equal tan FOV over 2, but it doesn't, right? So pix width times multiplier equals this, which means that pix width over 2 tan FOV over 2 is equal to the other way. It's tan FOV over 2 over pix width 2 times this is equal to the pix width multiplier. Yes. And then what does that give us? Then we can just take that and apply that as like our x value. Yes. Uh, but then it has to be like offset from the center. So like something like this, I think. That feels kind of right. That feels kind of right. Okay. Let's start splitting out some functions here. So we're gonna do like calculate unit vector. We can start with it being like totally wrong too, and then start approaching the right answer once we have something visualized. It's better to just get like something on the fucking screen, I think. From click. How's dog? Dog's doing great. Thanks for asking. Um, so mouse pause here is going to be some sort of like mouse position, and then our window size is going to be probably like a U size. Maybe we can do this as an F32 for now. So can we just copy paste this? So we said, which means we need FOV here. And then do I agree with this still? Pix width times multiplier over 2 is equal to tan FOV over 2. Yes. So then to calculate the multiplier, we flip the 2 up, we flip the pix width down. Yeah, that feels right. Mult is equal to this. Uh-huh. And then we say ret is 001. Ret x is window size over 2. X minus, I think I got it backwards. Times mult. And then ret1 is the same but with y. And then we return the normalized version of this. That's like a maybe. So then on click, I guess we'll do like on right click maybe. Because we're using the left click for camera movement. I guess we could just switch this to right down and right up. And then do mouse down here. Unit dir is equal to calculate unit dir from click with the last mouse position. And our FOV. And then we know that it's 800 for now. We'll fix that later. Okay. So this should start like moving the arrow around. Okay, and then we just need to kind of rotate around so that we're like looking. So if I click like fully on the left side of the screen, oopsies, it's not behaving the way I want. So I don't think. It might be. So this arrow, I guess, is technically representing like the field of view of the camera. So if I click on the full left side, he's kind of like versus full right side. He's kind of saying that this is like, we might have this backwards, but that is like the angle of the field of view that I'm shooting at, which feels like it could be right. And then I click on the very top. It's down here. Yeah, it just feels like the minus is in the wrong direction. But that might be right. So what should we see here? We should see, like, if I zoom in and I click in the top left corner, it's like the angle there should be way smaller than if I zoom all the way out and click in the top left corner, which is true. I mean, that might be right. So I click like dead center, and it should be directly along the z-axis, which it is. Yeah, okay. Yeah, so I think that what the arrow is showing now is like I have some field of view, and I click like on the left edge of the screen, and it points along this arrow. And I click on the right edge of the screen, and it points along this arrow. That's like that's not guaranteed wrong, right? We do see it kind of like navigating towards left and right as I go left and right, and we see it going up and down as I go up and down. Which, sure, fuck it. And then yeah, we see as we zoom in, it gets smaller. So like, sure, we'll kind of pretend that's right for now. Okay, so that means this is not calc unit vector. This is calculate dir click direction. I think is a better name for this. Okay, which means that now we just have to do like the rest of the math, which was what? We have like some direction as well as some vector to the center of the guy. And I guess we want to do all of this in world space, not camera space. So we have the direction in camera space, and we need to convert it to world space, right? So how the fuck do we do that? We invert the rotation component of the viewport transform before perspective is applied. Yes, which we can do. Kind of, hand wavy. Quaternion. We're not there. We're trying to get there. We are trying to build a visualizer for quaternions, and we haven't actually started using them at all yet. But we'll get there. Right now, we're just trying to do anything. Okay. So no, we can't just invert this thing because it's not. It's a 4x4 matrix. God damn it. But we can just do the inverse operation. Because viewport transform. So it's like viewport, like camera to world. Camera to world rotation, I guess, is what this is going to be. No, this is going to be a transform. And I guess we just do these three operations in reverse. So we start with the translation, and if we translate it by 5, we have to translate by -5 to undo it. Then if we did a rotation of x by x rotation, we should just be able to do the inverse of that, then the inverse of this. This is like, I'm quite unsure about this. And then Then what does this give us? I guess we don't need. I feel like I'm missing a piece here. No, no, it's fine. So we're going to try to get this direction in world space, which means we actually don't care about the translation at all because rotations are all the same. Yes. So in reality, we can take off the translation component. Yes. And this is going to be rotation. Okay. We're getting somewhere. So here, we're going to do this. Then we have the unit. We have like the clicker is this from camera. This is going to be like camera to world rotation. We're gonna have to feed him some vector, which is gonna be, you know, this thing plus the homogeneous coordinate, which doesn't have an effect in this, which is fine. Uh-huh. So this is the homogeneous coordinate, and then we need to just drop the fourth component here. Yes, yes, surely. So we're gonna like click dir world homo 0 and 1 and 2. And then here we're just going to do a quick std debug assert that like the homo coordinate of this guy is like equal to 1.0. He shouldn't have been touched. Or he should at least be very, very close. Okay, so then we have this click direction. We have the center is 0. So the offset from we just invert the camera position. Do we have the camera position? Not really, huh? This is like we know that the camera position is like 5 meters back on some axis. Like, as we are like rotating the camera around, he's always 5 meters from the center, but then we've just got like some like rotations applied as well. So how do we find in world space where this is? This is like we just put 0, 0, 0 through the transform and see where it ends up. And then what does that give us? What does that give us? So I'm like here. This is the center of the world right here, right? This is if I put this through the camera transform, we know that this is just going to be 5 along z, which does not help us. That does not help us at all. Right? This is just going to be 5 because we're 5 meters away or whatever, like 5 units away. So how do we find This. We have to go through, like, we got close to this concept before when we made camera to world rotation. uh it feels like we're so close. We just need that like 5 meters to be in here as well. Yes. Camera to world transform is, we said we do like the actions that we did to do the render backwards, right? So the translation here is the last step. So we do translation. Then the rotation. And then if we put the point of 500 through this, then it gives us where we are. I guess. I think that makes sense. That feels like it makes sense. Right? Or 0051? Right? Surely. This is in the homogeneous coordinates, though. This is going to be we just divide each thing by the homogeneous coordinate. Okay. This feels like we're getting somewhere. It feels like we're getting somewhere. So this is like homo 0 over homo 3. Yep. Okay, let's just see if this makes sense. Right? Let's start here. So std debug print camera pause is this. Yes. And then let's just discard the clicker. All right. Okay, so we're hoping. I am like on the z-axis right now, right? I should be like 5 meters away on the z-axis-ish. Fuck. 0. It's 0 everywhere. What have we fucked up? What happens when we do view times vex 0001? Note the 1. What is the translation from the origin to the camera? Blah, blah, blah. Yeah. That sounds... I think I was like thinking about that. I must have something backwards here. Oh, this would be 000, not 005. So I click here, and we're at -5, and then I look straight from Y now, and we should be at approximately 5 up on the Y-axis. Then I look from the X-axis here, and we should be approximately 5 on the X-axis. And if I spin all the way around here now, this should be -5 now, which it is. This looks like it's working. Then if I come from here, we should be at like 5 over root 2 in each axis. It's hard to even it out. But that sounds like it's kind of right. Yeah. I think that this is working in terms of figuring out where the camera is. I think. So we have that. And I guess here, can we then start looking at the click direction? Okay, so what are we hoping to see here? So here I'm looking at like the XY axis, right? And I guess we're hoping to see something where if I click in the center, it should be like almost entirely Z, which is what we're seeing. We're seeing 1.0 here. Then if I click up towards the top, we should see like Y with Z decreased a little bit, right? Because like the direction is like kind of trended up, but it's still going to be mostly Z because the zoom level. If I zoom out more, we see that the Z is decreasing more. And if I zoom in here, it's like the farther in we zoom, the more biased towards Z it gets. That makes sense. Then we rotate and we do the same experiment with the x-axis now, right? So what we should see is that we're mostly along x. If we click in the center, it should be like 1.0x almost. And then we get farther from here and it becomes like kind of, here it's like a little bit of x, a little bit of z, but very little y. This looks right to me, surprisingly, very shockingly. This is behaving the way I would expect. So now we look along the y-axis. Mostly, but we're kind of rotated, so like maybe like this. So this should be almost all y. Then like we start adding in some x, but z is still mostly small. Then we start going up in z. Yeah, I think that's right. I think. Cool. So now we just have to do the rest. And from this, it should be relatively easy, right? We just follow the steps that we or Kirsten told us earlier that I agree with, right? So we need our perpendicular direction is going to be basically like I actually don't know how to calculate that because it's in 3D, which is confusing. So we have like, we now have the direction of the ray. We have, this might be backwards, the camera position. I might have to put negatives here because we're saying we have this arrow, I think, and we want the other way. So let's just kind of, we can call this camera to origin. Okay, so now we have this. This is C to O. This is dir. So I don't know how to get like this anymore. Do we even need it? We must. I mean, maybe we just do this in 2 axes. So if we're like, you know, going through like the top left of this sphere, how do we calculate the collision on this point in the surface? Right, this makes sense for 2D. We could break this into multiple 2D problems. Maybe? No, I don't think so. I don't think it works that way. So we have, it's also correct for 3D, but it took me some time to convince myself of that. I guess what I'm confused about is I don't know how to get this number 3. But maybe I'm a dumbass. So we have some arrow going through here. We have, because you need to know. Oh, you just project onto the normal? There's some projection you do to get this, I guess. So you have like, you have this line. You just no, because it's part of a right angle triangle with the other sides being length, offset, and proj. But like, don't you need a 3D normal to get this? Maybe you don't. Oh no, yeah, you're right. You're right. You don't need any 3D anymore. Once you've gotten to this point, you're working strictly in 2 dimensions after you've done the projection. Yeah, yeah, I agree. I agree. I was thinking that like you need this 3 in like 3D space, but you don't. You only need its length. Yeah, 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 you're right. God, it's so hype having someone who's like better at reasoning about math than me in chat. It's so hype. I just don't have. I get to be a little bit more loosey goosey with the math. With the math, which, as my youth pastor said, loosey goosey, no fun for anyone. Dude, can you imagine? Can you imagine telling that to a bunch of teenagers? Don't have sex because it turns you loosey goosey, no fun for anyone. Just like what the fuck? Man, I think about that once every couple months. I guess every time I've used the word loose, I just think about that, like this interaction from like 15 fucking years ago. Dude, just it's so funny. Oh god. Sorry, this is a programming stream. Okay, we gotta focus. No, truly words to live by. Yeah. Oh man. Okay, so we have one. Two is easy to get. Uh, so we'll say, dude, can we? I don't know how to name this. Uh, I guess we'll just call it proj like you called it, and we do like a dot product of camera to origin onto the click-der world. So that gives us this guy is a distance. Uh-huh. So we have this now and this guy. So it's length length of the like camera to origin length is length of camera to origin like this, which gives us this guy. So 3 here is the other part of this. So, you know, perp is the square root of camera to origin length times camera origin length plus proj length times proj. This gives us this guy's length. And then how did we say we get 4 here? We have perp and radius. So radius is 1. So we can do a squared plus b squared equals c squared again. A squared plus, so we have like 1 squared minus perp squared is over squared. Yeah. 1 minus perp times perp, which is this. So we can just call this perp 2. And then we can take the square root of this guy. I think that's right. I think. And then distance in this diagram is proj minus over. And then we do camera. I guess we need the camera position as well to like basically start here and move in that direction. We need to do like camera position plus the direction of movement times the distance. Yes. Happier staying with the horrible naming. I mean, I just like with math, you always have like these numbers that like It's so hard because they don't fucking mean anything, right? Like they're labeled things that you need in order as intermediate steps to get something else, but they're not like a thing, right? When you're in programming, you're like, I have like this thing, and then I have this thing, and then I have this thing. Here we're just like, I just want this number, and this number is like the opposite of this triangle that helps me get to this other triangle. And it's like that's not like a thing you can call. You need to like draw a diagram in the code and then put letters on the things and then reference them by letter. It's the only way. Uh So this is, I guess we do this. Camera pause is this guy. Camera to origin is camera pause times -1. Okay, so then we can do camera pause plus clickter world, sure, times the distance. Okay, and this should just be like the unit direction now? Is this? Oh, that's a maybe. Let's see. Work. If this worked, that's so fucking hype. So I am now kind of happy with the names, by the way. Over is for overshoot, by the way. Yeah, that makes sense. I thought it was how much over we're going to move back, but overshoot works as well. Yeah, I spent like half the time on that diagram making the names. Nice. Okay, so whatever we did is wrong here. We're getting a lot of nans, so we're going to have to break this down. I guess we just print everything. Okay, let's start with, okay, camera to origin. Camera pause. Oopsies. Okay, what else do we have in here? Camera pause, prod, dude, I don't really know what I want to see. I guess we just fucking print everything. So what's the macro here? Deleting words to debug, print, yank in this, paste, and then paste, and then there we go. And then we forgot the number part. And then can we just do like a couple new lines just so that I don't get confused about like what is part of what? Okay. So what do we got here? We got camera pause is 0, 0, -5 on Z, which is true. Camera to origin is 5 on Z, correct. Projected, it should get like smaller as we get farther away, which is working. Then perpendicular squared here looks wrong. Right at the center, it should be 0. So perp 2 looks like it's wrong because we were supposed to do camera to origin length. Oh, because this should be minus. This should be minus because this is the hypotenuse. All right, let's see if that makes more sense. Hello, hello. Wait. Oh, come on! Wait, okay. So it was working. I think that the rotation of the camera is backwards here. But when we were fully aligned, this is now tracing the mouse very well. So it's our rotation around the y-axis. Mm, yeah, I mean, if we align ourselves with the x-axis and then start like going over, it's pretty clearly just backwards, right? And then here, it matches up again. It's like I have an inversion over one of the axes because this is working on z in both directions. I think. Yeah, what is wrong with this? I'm obviously late, but LOL farts. Thank you for that. Yeah, what is happening here? Inversion over x? No, because when I'm here, it's working correctly. Is it just backwards y rotation? It could be. Although that doesn't make sense to me. Yeah, I mean, that's clearly not it. I mean, that fixed it. I just don't understand why. What the fuck? What? This must be. I must be canceling out a mistake somewhere else because this does not make sense. Oh, there's Is there some form of like y inversion that I'm not covering correctly? Like, is it like something like our Windows to? No, dude, I hate this shit. There's like something's backwards. Like, it does not make sense to me that we should rotate in the same y direction again. That just doesn't make any sense. Y up, y down. That's kind of what I'm thinking. But that doesn't really line up anywhere to me either. It could be that the calculation of the circle intersection is correct, and the conversion to the rotations of the arrow transform are wrong. Like, it could be that it's supposed to be a negative here. No. No, that can't be it. Okay, let's log uniter, which we are. Okay. So we are expecting negative z here. So this is okay. So when I'm like looking at this directly on the xy axis, I want negative z, positive x, positive y, which I am not getting. So my x-axis is inverted from the way I expect, or I was looking at this from the other side. So if I'm here, positive x, yeah, my coordinate system is like backwards from how I think it should be. I think that's a problem. So I'm expecting Z to go into the page, X to go to the right, and Y to go up. And here I'm seeing all positive, but Z's over here, right? Like I would think if all positive, the arrow should be pointing this way. So that kind of lines up with the way that it's broken. Um, which means that there's a negative on the x-axis here on the rotation for the arrow that's backwards. No, it's the click position calculation that's wrong. And so why? His Z position is inverted? Did I get the translation backwards? Translation 5? Do my world coordinates need to match? Wait, that XYZ is only for perspective transform. Do I think that that's true in the world? I guess I haven't defined a world coordinate system. Are we using standard OpenGL conventions for coordinate spaces? I don't know. That might be the problem. I suspect that that is related. So I think that my world is left-handed. Because the perspective transform is the guy who's inverting Z, maybe? I don't know. I know that my perspective transform is like fucked. My perspective transform, this is usually a negative number, and I flipped it because I like positive Z going into page. But then I don't know how like that lines up with everything else. We inverted X when we imported models. So I think my whole world is the wrong one. Left-handed instead of right-handed? I think I want left-handed coordinates everywhere. Whether or not that's what I'm doing, I don't fucking know, but I think that's what I want. Which means what? I mean, clearly there's a mismatch. I just don't know who's doing it wrong. I mean, it's likely that I fucked this up like 4 different times and we're like stacking errors, and that's how like anything was ever working. I guess in world space, what we can do is color we can color our axes differently for positive and negative. Let's do that, and that will help us. That will help us understand. Um, so let's just do red and green and blue are positive, and then we'll invert. We'll just like I don't know, do some like rotations for negative colors or something. Oh fuck, that doesn't help. We need to duplicate the vertices. So this goes 0. I guess we could just do it something like this. I don't know. So 0 is 0, then -1 is yellow, +1 is red. Yeah. We're getting somewhere. Yeah. Uh-huh. Okay, let's see if this looks like anything to us. Okay, cool. So now we have colors that help us understand. Right? So red, green, and blue, this is like the positive side, according to us. And my click position is -z here. This is... I actually don't understand how both of these are... This is -z, +z. -y, +x, that makes sense. This should be -x, -x. Yeah, so the z is flipped in our calculations. And that's because we probably just did something silly. Like if we just flip this, does that make more sense? Just take out that negative. So now here we should be positive, positive, positive. Which we are. We're seeing positive, positive, positive here. This should be negative, positive, positive. Yes. This should be negative, negative, or negative, positive, negative, 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 negative. Okay, so now the axes... Now we're close in that like where I click lines up with the axes, but then it looks like probably my rotations are the wrong way for the arrow transform. So let's just fuck some negatives on here and see if that kind of changes anything. Okay. We're really just kind of flying by the seat of our pants here. Okay, so here, aligned with Y, great. Aligned with X, wrong way. Or sorry, that's... Oh. Okay, let's think about this again. Aligned with Y, cool. And then as I go down, it's like any way he's rotating from around this like x-axis, it's going the wrong way on the first rotation. So we go to Y, and then that's not good. Okay. What am I missing? So we think that the unit dir is correct. That's what we think right now. Let's double check that assumption. So we have, first of all, our coordinate space, left-handed, that looks right. So green is up for Y, X is up, red is up for X, blue is up for Z. So that's lining up with how I expect to see it. Now, oh, I totally understand now looking at this, by the way, why people use left-handed coordinates or right-handed coordinates or whatever the fuck the other one is. The one where Z comes into the page. It's because if you wanted an XYZ plot, it will be like looking towards you. Which, fine, but that's not what I want. It's fun if you do your math differently than everyone else. It makes it so that you have to think about it more. We can use that as our excuse. So this should be in the positive, 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 which it is. So then the question is if we're in positive, 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 why is the arrow pointing the wrong way? It has to be in like our like look at calculation, right? Which is this arrow transform. So let's think about this. So we start with like, this is the x-axis, this is the y-axis, and we like rotate the guy around the x-axis by some amount, right? And if we rotate clockwise around the x-axis, which I assume we are, I don't actually know, but if we were, z would be going this way and we'd be in negative z land. Which makes me think that we should rotate in the other direction to get positive z. So now I click, very cool app. Did you code color paint? No. I'm working on an alternative, but we're not quite there yet. Right? This is my image editor. He can erase, right? But he can't. We're missing some features that are kind of required, but we're not quite there yet. Dude, what am I feel like we're so fucking close. I guess we don't really know what this rotate X and rotate Y are doing. So rotate X is rotating around the X-axis such that, so as we rotate to like 90 degrees, sine will be 1. Right? Which means that the Z value is positive if angle is positive. So we're rotating towards positive Z, I think. Sine pi over 2. Yes. Okay, so Z value is positive here if we're at Z1 if we rotate 90. Okay. So that means here, if unit dir, sure. So we're going to be rotated like by some angle towards positive Z. Then we are going to rotate around the y-axis such that what? So we have like Z, we're going to be pointed this way, basically according to the y value of this intersection with the circle. Then we need to rotate this so that X and Z line up. Right. So I think this is the problem here. So our rotation is based off of X, Z. We're rotating counterclockwise. I think we want to do so tan theta is equal to opposite over adjacent, right? So if we're at 0, 1, xz, we want this to be a rotation of 0, which means we want x over z, but then the rotation here is counterclockwise, which means that if we then start moving into negative xz here, that's the angle. And opposite is, okay, so say we're rotating to point towards negative x. That should be a rotation of 90 degrees, right? I mean, assuming that, what is rotate y doing? In rotate y, x, z is positive at 90 degrees. Yeah, so I feel like it's like, my gut says this should be z over negative x. I don't have like strict reasoning for that, but my gut says that's the answer. No, it was not, but we were close. Okay, so we are rotating counterclockwise. Say we love gut feelings in math. I mean, in programming math, it's like if it's good enough, it's good enough. If you have a gut feeling, it's like sometimes faster to check it than to do the math, you know? So let's see what happens right now if we click on the negative x axis. So on the negative x axis here, we're going to positive x. And then if we click on the z axis, he's pointing in the right direction. Yeah, it just feels like that second rotation is like backwards in some way. Negative x over z, maybe? Wait. Now what? Negative here? I'm so confused. So my understanding is that the y rotation is like, yeah. So here we're seeing that like it is always pointing. Oh, hold on. Here's our problem. When I click up here at y, oh wait, maybe this is right. So I click, I click. It could be the click projection is also wrong. Okay. Let's try making sure that we're only clicking on the center of the screen. That will help us bisect the problem, maybe. So here, we're trying to click. Okay. I feel like I'm close to understanding. So click on the center of the screen. Center of the screen. Aha! Aha! So if I click on the center of the screen, it works. Which means that now we have a problem with y value in the click offset. Which means this guy needs to invert y. Maybe. Yeah, that looks right. Let's go, baby! Holy fuck me, dude. Holy shit. Okay, now I think that there's an extra part of confusion here where we probably want to render the sphere. So if I click on like the very border of the sphere, I think it's doing what I want. Right? It's kind of like under the mouse. But how come as I click around here, it's not following exactly where I click? Is this guy correctly scaled? Z is 1. Transform looks right. I would like to maybe render the... Yeah, can we try rendering the circle in some way? Does that help us? I think so. Do we want UV sphere or probably the icosphere is better for this? And maybe we just up the subdivisions. Sure. And then export GLTF. And this is sphere. And we only want to export visible for the sphere. Include visible objects. Maybe even selected objects. Okay, so now can we load that guy? And can we render that with sphere model? We are going to need to reduce the alpha for this guy. Oops, we need sphere buff as well. The model needs to be uploaded to the GPU. And so then we need to do this with sphere buff. Okay. And then we want to change. This guy wants the viewport transform only. The sphere should not move. How the fuck did we manage that? Oh, I doubled up. Okay. Okay, and then I guess can we change it so that the we probably want to use sphere program, and the sphere program is going to be the same vertex shader but a different fragment shader. Okay. So our sphere fragment shader is going to be like this. And then we're gonna write source sphere fragment GLSL and open it. And we're gonna change this to discard the normal and just be like, make me like green at like half transparency. Maybe. Okay, but the transparency isn't working, which means that we need to turn. We need to turn on alpha blending, which we haven't done. GL alpha blend, GL blend, I think, and blend funk. Which we use such like 1 minus source. What are the blend functions? What's like I don't know what I usually use here. I thought there's like some sort of like 1 minus alpha or something that is you're supposed to use, but maybe we just do this, we'll see. This feels like it's still not working. 0 alpha, please. Yeah, this is clearly not working. Open GL enable alpha blending. Bump 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 bump. Yeah, let's go to the web the noob site. Thank you. This is what I need. Blend. Blend. Where's the like just give me the fucking GL enable GL blend. Is that not what I did? Okay. Is this bound to like some program or something? Sphere prog, sphere buff. Am I fucking stupid? Oh, wait, yeah, this is what I was looking for. This is what I'm used to saying. Whether or not this is correct, who fucking knows? But that's at least the words and letters I recognize. What's going here? Oh, is it a blend equation? GL blend funk. Ah. I see you're taking the Bartholomew approach to this. It's very interesting. Who's Bartholomew? And is this are you saying that it's just good like I'm just fucking guessing? That I would agree with. Okay, so this is clearly wrong. Why? Why does it look like this? It's like we need to sort the triangles, right? The problem here is that the we need to draw back to front. I would have hoped that like backface culling. Oh yeah, that sounds more likely, huh? Because I was gonna say it should seem like the OpenGL pipeline should sort the triangles for me. Because like you need to know the viewport transform in order to do the sorting. And it's like why would you fucking do it that way? Yeah. Uh, OpenGL backface culling. Bump bump bump. Yeah. Uh, that feels like it could be it. Yeah, that looks more reasonable. This is just a circle. That's kind of funny. I was kind of hoping that I was kind of hoping that you would see like more transparent like darker around the edges because of more like I would think that there would be like more stacked things here, right? So it looks like at the very least the arrow is in fact lining up with the radius of the circle, which makes me think that my click position calculation is wrong. You know, it seems like the calculation of where the edges of the circle are correct. Right? Like if I click off the sphere, then it's like clearly just like starting to lose its shit. Although maybe not in a way that I expect. So these numbers are turning into nans, which is kind of surprising. I don't think I would expect that. Oh no, that does make sense because this guy's becoming negative. So that makes sense. So what are our options here? Right? Like, have you done quaternion interpolation? Well, so the title was kind of indicating that this was supposed to be a visualizer to help us understand quaternions. We were going to make this widget and set this to be the IJK component of the quaternion. But instead, we've kind of ended up spending a lot more time with just trying to render this like debug view. Right? What I was imagining when I started the stream was that we were going to try setting quaternions by pointing the axis in some direction with some slider for like real versus imaginary, and then I wanted to like see if I could like generate our like WXYZ out of like these two things and like see how they affected some like thing on the screen, right? But we've got like so rabbit holed on just doing something as simple as like point arrow at where I clicked. Understanding rotations in any form is time well spent in this context. Though, yeah, I mean, I'm not really that shocked. It's like it's fine. I think that like like we're tackling things like ray casting into a sphere and figuring out where we clicked. I think that's like we should just be better at like our 3D math anyways. So it's fine. It feels like I'm missing a square somewhere. Make a ghost arrow where you hover your mouse. I mean, this mouse. I mean, I don't think that helps me. There could be like a length mistake in here somewhere as well. I still can't get over how translation in 3D is input as a shear in the fourth dimension. What is about fourth dimension that we can't understand? In what context? Implemented by who? Are you talking about like translation matrices? Because I don't think that's true. But you might be talking about some context I don't understand. Okay, can we make it so that like we're like almost perpendicular to the blue axis? It is like not quite there yet. 3D translation matrices are a shear. Okay, I mean I could be wrong. Because in 2D you do the shear in 3D. Like, is it not? So my understanding of like 3D like the transforms, the 3D transforms. Oh, I think I understand what you're saying. Kind of. I feel so like your coordinate system in these like 4x4 matrices is like kind of fucked up, right? You have XYZ as like 3D. These are like your like 3D vertices, your 3D like components of your vector, right? And then W is like X over like this is just like a divisor for the other guys, right? So like I'm not really convinced that this means that like translations are implemented as a shear. They're just like, hey, everything is scaled by this value, and usually your scale is 1. So you put like your X translations over here and they get multiplied by 1. That's like my understanding. And like my understanding is like this is just like a trick so that you can do perspective. Having the divisor thing here so that you have a way to do like, you know, X scales with Z. That's my understanding. Matrices only do linear transformations, and translation is not one of them. 4D matrices allow us to do affine transformations in 3D. I agree with that. I just think that claiming that like W is like a thing in the fourth dimension that we're using, it's like I don't really think W is a fourth dimension here. Unless you're claiming that like doing perspective shift is like the perspective is applied as some sort of fourth dimension shear, I could like maybe see that argument. Visualizing XYW, playing with it, especially with points projection onto XY plane out W because 1 gives a good intuition. Okay. I mean, I trust you. So maybe. It's just in my mind, it's like W is like not even in the same coordinate system. So in my mind, it's like there's just no geometric like relation to this thing. But maybe that's just like a naive way of looking at it. Okay. So let's look at our math again here and see. So we're like calculating maybe it's like our perp is getting too big too fast. Most graphics programmers have that it's a hack mentality and it's fine. The theory can get deep if you want to go through it. Go to it though. I mean, yeah, I guess like the argument, how do I say this? From the 3 blue 1 brown videos I've watched, which isn't a lot. I'm not like that into math. I'm like a little bit into math, not that into math. like more so than the cashier at the grocery store, and less so than people who went into university to do math. Probably less so than a lot of programmers, right? But from like the videos I've watched, the 3 blue 1 brown thing is always like, hey, I'm going to show you a way that this makes sense that you didn't know about. And so I guess the argument is like, you do something that makes the numbers work. Just fuck it. Do something that makes the numbers work. And then later, we can find what that actually means. And it does mean something. Right? So you guys saying, like, this is a shear in the fourth dimension. It's like, by some definition, probably yes. But it doesn't have to be thought of that way. Maybe. Right? It's like you have some geometric explanation for why the numbers work out, but like, you didn't need that to get there. Maybe that's how I should be thinking about it. Relativity was basically hack the speed of light until the numbers work. Very rich theory came out. Yeah, yeah. Like you do you fix the numbers and then like catch up to why the numbers work that way after. So if they work, I guess the like what like if the numbers work, then it's not a hack. Really, it's like revealing something that you didn't previously grok, which is fine. I'm just going to stay in the camp of I don't need to understand it more than like the algebraic way that it works out in this context. But okay, I see where you're coming from now. It is neat. Okay, back to trying to solve this shit. Why the fuck? So is like the amount of incorrect in world space, it feels like kind of consistent with my zoom level, right? So I click here. If I'm like clicking like right here on like the green to blue transition of the arrow, it is staying there. And if I zoom in over here and I click in the same spot, the arrow doesn't really move, which makes me think that like the calculation of field of view from pixel space is working correctly. I guess we could try to do the math and check if we think the angle that's being calculated here is correct. Right, so if we say like dead center on this guy, we should be able to what? Like we should be able to calculate where we think we should be intersecting with the circle. Let me think for a second. Maybe we want like to look at the click direction from the context of the camera. Maybe that helps us in some way. Do you intersect with the correct side of the sphere? Oh, that's a good call, huh? That does line up with how it's failing. Yeah, you know what? I bet you're right. Although, how could I have got that wrong? No, I don't see. It seems like that shouldn't be possible to fuck up that bad. Although it does look like what you're saying. I don't understand how you could fuck it up that bad with the math we did. It would be so hard. Because, like, we did, like, a projection onto this. Yeah, it would just be so hard. Unless we did a plus somewhere that we shouldn't have. No, here. There's no way. That does, like, how? How would it be like that? Are we logging camera to origin length? Camera to origin length should always be 5. Which it is, so that's correct. I think that it would make sense if our direction vector was wrong. It seems like this being wrong feels like what it is, because we can't be getting this wrong. There's no way. This is 5 all the time. We should probably double check that the length of that thing is 1. It should be, but like we should just be sure. Click dir camera Are we logging that already? No. And then can we also log the clicker length? So this should be one length all the time, which it is. We're seeing like a 1.0 basically no matter what. So that's good. And then the click direction in camera space, here it's like directly along the x-axis. That makes sense. And then here it's like, oh, you know what? How the fuck is this happening? Where when I click on the very edge of the circle, it's like going past 90 degrees. That shouldn't be possible, right? I click here, I click here. We should never be on the back side here. So that's a good clue as to the problem. Is that like at some point like here it's on the correct side of the axis, and then at some point I get like past it. And that should never fucking happen. Ever. Ever, ever, ever. So can we look at like the unit term? We don't even have to picture. We should be seeing somewhere a negative sign is flipping. X, Y. Yeah, here. No. Oh, so that's interesting actually. We're seeing like Z is negative all everywhere here. Negative, 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 negative. But then here, oh no, it's positive. That is, okay, so we are seeing, yeah, it's like if I get really far along this thing, the Z becomes positive. Which is a good clue as to the problem. It means that is it related to the fact that the click turn length is 1? No, okay, that shouldn't be it. So projecting this onto this. So it's like somehow we project onto the direction vector, and then when we move along that distance, this is somehow larger than the distance to the XY plane, which seems fucking impossible. So can we confirm that here? So here, distance is like -5, -5, -4, -2. What the fuck? What is distance here? How is it -5? Oh, because projected minus over. Okay, what about like projected? Um, thinking. So from top down, here's the circle, here's us. We have some field of view. And when I click on the very right edge, I guess like our field of view is like kind of maybe fatter, right? Now we click here. Somehow, like if this distance is 5, this is always 5 right here. It's like the z component of this intersection is bigger. Can we let's I would love to show the position of where we clicked from the perspective of the camera. So can we do like click lock camera is click dir camera times the distance. Let's see if that gives us any insight. Do we expect negative dist ever? Oh, that's a good point. Yes, because it's in world space. So like if I'm on this side, oh, it does seem always negative. I thought it was because of it being in world space, but now you've kind of like got my eyes on that as well. Okay, wait, let's just, okay, so in click location camera, so here he's like at like -6, -5. Yeah, it does seem backwards. Does seem backwards. Is the editor series over? Not necessarily. I'm still working on it. I did some work on it like the other day. But I try to focus on whatever I'm enjoying at a given point in time. Camera to origin is we take the camera to world transform and we apply 0, 0, 0. Uh-huh. Oh, maybe this is backwards? Camera to origin. So the camera is at... It's hard to see with the fucking green sphere. Hold on. We definitely have some wrong numbers to debug. Okay, so the camera starts at -z. Okay? So when we click here, camera to origin is backwards in world space. This is supposed to be in world space +5. So how do we fuck that up? Oh, because we inverted this thing? Ah. Because we inverted something when we shouldn't have, because we thought it was world to camera, not camera to world. No. Camera to origin. Is that what we're printing here? Camera to origin. So this should be positive, which means like these are inverted. Although I just don't really understand why, but that's okay. We'll just see if that makes things line up a little better. And then can we undo that? Well, okay, let's see now if the numbers are right. So this should all be positive, 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 which it is. This should all be positive or negative, positive, positive. It is. And as we get over towards the right side of this thing, this is becoming like X value is becoming less negative. Okay, and then is my y value flipped as well? It is, which makes me think that here we just need to switch some negatives around. Okay, so that fixes it. That looks a lot better. Now it's always pointing exactly where we click. And so when you said, whoever said that I was going through the sphere and clicking on the backside, I think you were right. And also when I was like, it's really fucking hard for us to get it wrong that way. It's like, I think it was really hard to get it wrong that way, and we did it anyways. I like still don't even know how we managed to fuck it up that bad. But we did. Alright, this is kind of hype. Can we turn the sphere back on? I don't know if I like the look of this green sphere on top. Right? I was kind of hoping to see something that was like a little bit more dynamic. So I think I'm just going to take this off. And then yeah, I mean, that's pretty good for now. That's pretty good for now. It's 3:30, so we've been streaming. We're like half an hour before like target time. I don't really know where the next piece would be. I haven't really thought this through. I guess it would be like actual quaternion stuff. Because now we have a way to like generate the XYZ components of a quaternion by clicking on this, which is pretty hype. But it feels like this makes sense to just continue on tomorrow. We're at like a natural breakpoint and like a natural starting point for the next stream. So once again, I was too ambitious with my title. And we didn't do any of the quaternion stuff that I thought we would be doing. But that's okay. Make sure to do homework and watch the video. Right, of course. So I think we call it there. I thought this was going to be a happy hour stream, and then I was going to do like a short version, like a short recording for the main stream for the quaternion stuff, but I guess this probably just goes on the main channel. Or like this gets posted on YouTube, so it'll be up there. If you like what we saw, we stream most days at around 12:30 Pacific time to 4 o'clock Pacific time. It is 3:30 now, so anywhere between 3 hours ago and half an hour ago is when you should expect to see us. Right now, we're kind of working on this project of trying to get our little guy rendered into a game. Right, so we have our little animation of this guy. Wow, look at him. He's so pretty. And then we've also been working on our image editor. I've got a couple other things coming down the pipe, but I don't think that they'll be started soon enough to be worth talking about. So next up is like trying to figure out, we're going to do some quaternion stuff and then try to figure out how to apply those like rotations to the armature of this guy in our model. Right, so this is the motivation between this thing, is we're going to try to like take this animation and put it into our game. So that means that we need to understand how to like fucking work with the rotations and shit. So if you want to see that, we'll be back next couple days. We're working on this stuff, so check it out. Anything else to say? No? YouTube, peace out. Twitch, let's find someone to raid.